Okay, good morning. I hope I am audible.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Okay, so in previous lectures, we discussed about spectral signature, um, and we started with the spectral signature of vegetation. So if you see the this reflectance versus wavelength curve for the vegetation, then a different part of the vegetation, like when we consider the leaf pigments, cell structure, and water content. Okay, so the leaf reflectance is governed by these three components, and the part which you need to remember, like in the visible spectrum, the dominant component that affect the reflectance is leaf pigment, while when you analyze in near infrared band, so there is the role of cell structure. And finally, when we talk short wave infrared, then water content plays role to govern the leaf reflectance. And as you see in this plot, there is a valley at red, then there is a red edge. If you move from red to near infrared, there is a sharp transition from very low reflectance to high. We call it red edge. Then within the visible and near infrared band, there is a valley at red. Okay? And in the visible spectrum, the highest reflectance we get at green. When you analyze the reflectance versus wavelength curve within short infrared band, so there you can notice three valleys, and they are due to the water absorption band. And I told you, you need to remember those wavelengths where the water absorbs the energy. Okay. So at the red edge, you can see that there is an abrupt change in the reflectance from when you move from red to infrared. Okay. And the red is, you can notice, within 0.7 to 1.4 micrometer. Okay. And when like when we analyze the reflectance, when this curve enters the near infrared band, then reflectance raised to 40 to 50% in this region. Okay. So this is the region why for the vegetation mapping, are vegetation related studies. Okay. The spectral band we select in NIR, near infrared. One spectral band we select in NIR, and another spectral band we select in red. Okay. So why it is so? Because in the red band, you have a lowest reflectance, while in case of NIR band, the reflectance is 40 to 50%. Okay. I will discuss about this later on when we'll see the data processing. Okay. Why this NIR band and red band is important? For identifying the vegetation, to for the other vegetation related studies. So red, again, this is a concluding remark over here. At the red, there is a valley. Okay. And in NIR band, we have a reflectance 40 to 50%. Okay. Due to these regions, we select NIR and red band for further analysis of vegetation. Okay. So multiple layers of leaves provide opportunity for more reflectance after the transmittance. The layers we have already discussed, like the component of leaves, okay, which govern the reflectance in a different spectral band, like visible. Then we have a NIR band. Then we have a microwave. And there is a water absorption band at 1.4, 1.9, and 2.7 micrometer. So let's say if someone asks, can we do the remote sensing at 2.7 micrometer? We do not select any spectral band around 2.7, 1.9, and 1.4 micrometer. Because if we discuss over here, it as a water absorption bands. Okay? It means in the atmosphere also at these wavelengths, the energies are trapped. Okay, so energy that pass through the atmosphere, okay, at 1.4, 1.9, 2.7 micrometer. If you analyze this atmospheric transmissions versus wavelength curve, so there also you can notice the values at these three wavelength. Okay, so concept is same, like it's a water absorption band. There is a kind of trapping the entire energy due to the resonating effect. So wherever the water will be the component, okay, the behavior of water will be same. Like if water is a mix with some other object, let's say we can talk in the rainy season, if there are the water logging, okay, and there is a water logging and you are doing remote sensing at 2.7 micrometer. Even you are trying to sense at 2.7 micrometer using some sensor, okay, so what will happen? You will not get the reflectance. Okay. Now we discuss the spectral signature of dry soil, and this red curve indicate how the reflectance changes with respect to wavelength in case of dry soil. Okay. Again, you can notice the value over here, just first, second, and third. Okay. It is again due to the, though it is dry soil, but we can expect some amount of water there. Okay. So there is a valley, and it is, and this valley is nearly matches with the wavelength at which we get valley for the vegetation. It's around 1.9 micrometer. Okay. Similarly over here, it is 1.4 micrometer. Okay. So in case of dry soil, the reflectant depends on the moisture content. What will happen if the water content will increase, then it will further depend. We'll see in the next graph. Now it also depends on the surface roughness, presence of iron oxide, presence of organic matter, etc. This value could be due to some other reason, because at this point we don't have a water absorption band. What is the difference between a spectral signature of soil and vegetation? You see over here, in case of vegetation, within NIR band, the reflectance is very high, 40 to 50%. Okay. While in case of soil, it's a monotonically increasing plot. Okay? But at certain wavelength location, there is a valley. So the significant reflectance we get in mid-infrared band, you can say it's more than 1.3 micrometer. Okay. While if you analyze within this 0.7 to 1.4 micrometer, the highest reflectance we get from vegetation compared to soil. Now we'll see the effect of these like iron oxide, organic matter. So these constituents, how they affect the curve of this dry soil reflectance versus wavelength. So one by one, we'll see that. When we analyze the moisture content, you see over here, and just see overall the moisture, due to the moisture content, if let's say it is 5%, then the entire curve shift downward, okay, where the valley location further depend. Similarly, when you keep on increasing the moisture content at 20%, you see over here, due to this valley, it's at 1.9 micrometer. The absorption band is notified over here, it's 1.45, 1.92 micrometer. And it is an important parameter due to its dynamic nature and large overall impact on the soil reflectance. So overall, if moisture content will increase in the soil, then entire curve will shift downward. It means the reflectance component at every wavelength will decrease. And further, this at the water absorption band, 1.4 by 1.92 micrometer, you can see the significant decrease in the reflectance. Now, soils from different natural drainage classes. Okay. So if soil is better drained, they are more reflective. Okay. It means if you see the curve over here, so the first plot indicate the better drained soil, while in the second case, the poorly drained, it means there are the water content, and in the third case, it's very poorly drained. You know that like in various classes of soil, their drainage capabilities vary. Okay, so the soil that is better drained, in that case, you can expect more reflectance compared to the poorly drained soil. And it is evident to this plot. Now the reflectance from dry soil versus wet soil, and it all depends on the molecular arrangement. So in the first figure, if you see over here, in case of dry soil, even within the bulk, the reflected component comes out. See over here, let's say at this point, it the incident energy is transmitted within the soil, but here it is further reflected back and it goes out. So it can constitute the part of reflected energy over here. Okay, but what happens, and it is due to the obviously it's specular reflectance, and if we see this second plot over here, this the composition, internal molecular composition in case of wet soil. So within this gap, there are the water, they are filled, okay, and they are filled with water molecules. So what happens? Once the incident energy that is transmitted inside the bulk, that is a soil, okay, what will happen? It will be absorbed, will be trapped by the water. Okay. So in that case, what will happen? Like you will not get the reflected the energy part that is transmitted within the bulk responding to that component. You can't get the reflected value. So there will not be the reflected component from inside the soil. While in case of wet soil, there is a air space, and within the air space, volume reflectance takes place, okay? And you can expect uh, the reflected component within the bulk. Okay. So we have over here the conclusion that we derive based on this discussion. In case of dry soil, reflectance is a function of specular reflectance that happens and internal volume reflectance. The reflected component from the bulk material that is inside. Okay? That is called as internal volume reflectance. When the sensor sense the upcoming energy, so there is a component from the specular, that is from the surface, as well as there are the components from the inside of the soil. But here, in case of wet soil, the reflectance is only the function of specular reflectance, and that is from the surface. All the transmitted component will be trapped. So obviously, in case of dry soil, the reflectance will be more compared to the wet soil. When we analyze the effect of iron oxide that is present in the soil, then this is the primary cause of the red colors in the soil. Red soil, if you see that in the red soil, iron oxide contents are present. So this is a broad absorption feature centered at 0.9 micrometer is attributed to iron oxide. So here, due to the iron oxide, this is iron oxide absorption band, and it is at 0.9 micrometer. Okay. Now, for the organic matter, like when we consider the mineral soils as the organic matter, this content increases, then soil reflectance decreases. Okay. Further, when we see the particle size distribution, then the larger diameter particle size exhibits pronounced interstitial voids. So if interstitial voids will increase, then what will happen? Who will tell me?
Sir, please pardon the question.
The question is, if when we analyze the soil at the particle level, okay, and in case of larger diameter of the particles, that constitutes soil. Okay. So in that case, there are the pronounced interstitial voids. It means this gap. They are larger. Okay. Then what will happen? Got it. Okay. So these are the interstitial gaps. So they are the voids, and it is due to the larger particle diameter. Okay. Second case, when we consider the small particles.
Sir, you are on slide number 52, isn't it?
Pardon? I'm
Sir,
right.
are you on slide number 52?
I'm on 55.
Sir, not visible. Green.
Yes, sir.
It's 52 here.
Is it for all of you?
Yes, sir. It's 52 now.
Yes, sir.
Yes, sir.
Screen,
Yes, sir.
the screen is not visible at all.
Okay, kindly let me know. Right now I'm at slide number 55.
Yes, sir.
Yes, sir. It's visible now.
Okay. Should I repeat the discussion which we had with the previous slides?
Yes, sir. Yes, sir.
53 and 54.
Fine. So I hope 52, is it clear? We had discussion of,
Yes, sir.
related to the reflectance from dry soil versus wet soils.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So one terminology I'm referring in slide number 55 that I would like to discuss over here first before reaching to slide number 55. So if you see the molecular structure of dry soil, okay? So these are the particles, and when these particles are connected together, and there are the gaps. You see over here, we call this void, okay? And air is filled. So due to this void, you can expect the internal volume reflectance. Okay. So internal volume reflectance means once the incident energy interact with the surface of soil, immediately part of energy is reflected back, but uh, the remaining part is absorbed or transmitted. Okay. If you see this particular light component, it goes inside. Okay. And from this surface, it is reflected back. So within the void, the air is filled. So this reflected component get its path to comes out of the soil, bulk of the soil. I mean this internal part of the soil. Okay, and it comes outside. While in the case of wet soil, the void is filled with water. Okay, and once the transmitted component goes inside, this water absorbed water trap that transmitted component and doesn't allow it to further reflect it back, okay, towards upward side. Now, when we analyze the effect of size of the particle on the reflectance, okay, then if we decrease the particle size, let's say now these particles are small in size, then what will happen? In that case, the void volume will decrease. Okay. Once the void volume will decrease, then what will happen? Can we get high reflectance or low reflectance?
Yes. High reflectance.
It is due to why if we get high reflectance from the surface,
The maximum number of whites. So when the particle gets smaller, the number of whites increases. So it will give the high reflectance rather than the large particle.
If particle size is large, then in that case there is a volume for there is a void. Okay. When you decrease the particle size, then what will happen? Soil will be closely packed and the volume of void that is filled with air will decrease. Fine. So in that case, you can say that, okay, the particles, they are closely packed. Then can you expect from the closely packed soil, due to the small size of diameter, can you get high value of reflectance or low value of reflectance?
Sir, low value of
High value of reflectance, sir.
High value of
volume is, sir, if volume is constant for both the situation and dia of particles are decreasing, then we'll get low value of reflectance because the net volume of void will increase.
Sir, is it depend on the void size? If void is more larger than reflectance is larger.
No, that is my query. You see, obviously, if you decrease the size, then what will happen? Then let me draw over here.
Sir, when particle size gets smaller, for the smaller particle size, when the particle get closely packed, maybe the void volume decreases, but the number of voids are increasing. And if the number of voids are increasing, there must be the increase in the reflectance.
Hello, hello, sir. So water is a strong absorbent of light. So in wet soil,
no, we are not discussing the water over here.
no, sir. In wet soil, the water molecule will be more, so it will absorb more light.
Please, listen. We are discussing with the soil, okay, and relationship of reflectance with the soil particle size. The first case, we have a large particle, like as I draw over here. Okay. While in the second case, we have a small particle, and obviously due to small in size, it is closely packed. And the query is, in which case we get high reflectance? The first one or second?
सर फर्स्ट पार्ट में टर्म रिफ्लेक्शन ज्यादा होगा तो किस
The second one.
हेलो सर सर क्योंकि वाइड्स मतलब क्या लार्ज नंबर ऑफ वाइड्स हैं और उसमें वैकेंट स्पेस बहुत कम है, तो एनर्जी कम मतलब जो इंसिडेंट एनर्जी मतलब थ्रो होगी उस पर, तो क्या नाम कम एब्जॉर्ब होगी तो ज़्यादा रिफ्लेक्ट होगी।
सर फर्स्ट में गैप्स ज़्यादा रहेगा तो रिफ्लेक्टेंस ज़्यादा होगा उसमें। particle size is big, then gap will also
Yes,
will be
so
more.
सर फाइनर पार्टिकल जो क्लोजली पैक्ड है वो ज्यादा रिफ्लेक्टेंस देगा।
नहीं, रीजन क्या है उसका? वो तो ये लिखा ही
रीजन
हुआ
ये है सर कि नहीं, रीजन ये है सर कि जो क्लोजली पैक्ड सॉइल पार्टिकल्स है उसमें नंबर ऑफ वाइट्स इंक्रीज हो जाएंगे। नंबर ऑफ वाइट्स इंक्रीज हो जाएंगे तो वो ज्यादा मतलब नंबर ऑफ रिफ्लेक्शंस ज्यादा होंगे उसमें।
See, when we were discussing about diffuse and specular reflectance, so there we talked about the surface roughness, is it? If you remember, HT.
Yes, sir.
Yes,
In the second case, the surface is more smooth compared to the first, is it?
yes, sir.
Okay. So, in the second case, due to the small particle size, the surface is more smooth compared to the first. Okay. And if you analyze the surface, there is not enough gap that trap the energy. Fine.
Yes,
So
sir.
what will happen? The transmitted component will decrease. We can say the absorbed component and transmitted both. Okay. Transmitted component, I mean to say that it's not very deep. Like in this case, if I say transmitted, it is a kind of absorbed component where light goes inside, but at this junction, just see over here, there is a air to solid kind of interaction. So the reflectance takes place, fine, at the surface. If there will be less void, what will happen? The internal volume reflectance will decrease. So due to a decrease in internal volume reflectance, from within the bulk of this soil, you can't get the outcoming reflectance. But there are two components. The first one is from the surface itself, okay, and second one is from internal volume. What will happen in this case when the surface is smooth? Okay, so due to the smooth surface, the transmitted or absorbed component will decrease, and simultaneously the reflected component will increase. As you see over here, the conclusion in point number 2. Like when there are the large particle size, then this increase the surfacial micro roughness. I'm talking about this HT. HT will increase, fine, compared to the fine particle sizes and presents many more light traps. Okay, these are the light traps over here. No? Similarly, due to the roughness, light traps are more to any irradiance. Who will tell me what do we mean by irradiance? Irradiance terms is used to represent the light, that is energy, falls on a certain material. Radiance means when that is generated from the source, it is radiance. Irradiance means when that energy falls on certain surface. So the finer particle sizes will exhibit greater soil reflectance. Okay, now the next component, that is soil mineralogy.
सर उसका रीजन समझ में नहीं आया सर। मींस कि क्या हमारा वॉल्यूम वॉइड का वॉल्यूम बढ़ने से रिफ्लेक्टेंस इंक्रीज करता है या फिर सरफेस रफनेस की वजह से ऐसा हो रहा है सर? ये प्लीज क्लियर कर दीजिए।
Just read the point number 2. Is it clear to you?
Yes, sir, that is clear. But sir, in last slide we have read that when the voids are increasing, the interstitial reflectance that is also increasing. If we decrease the size of the particle, then the particular volume size will decrease, but net volume size will increase. Then, if in increasing the volume size, volume of void radius will increase, then that should happen in a large one also.
If you see this example, there are two cases with the same particle size. Fine. The
Yes,
second
sir.
one, in place of air, there is a water because it is a wet soil. While in the first case, the void is filled with air. Fine.
Yes, sir.
And if you see over here, in this case, the dry soil reflectance depends on specular reflectance from the surface itself, okay,
Yes.
as well as internal volume reflectance within the bulk. Fine.
Yes, sir.
When the size will be small, the specular reflectance from the surface will dominate. Okay. Though there will be the less reflectance due to internal volume from the bulk, due to the from the internal side of the soil, but due to dominant effect of surface reflectance over here, the overall reflectance from the small particle size soil will be more compared to the large particle size. Fine. So we can say that
Hello, sir. So is there connection between wavelength and intercellular space?
No, that part we are not. We are discussing this at a fixed wavelength. I hope it is clear.
Yes, sir.
Fine. So when we consider the soil mineralogy, then in this case, there is a pure calcite. It is mixed with soil. So this has a strong absorption feature near 2.35 micrometer. Okay. And at 1.8 micrometer, there is absorption band due to the gypsum. Now we discuss the spectral signature curve of water. So water absorbs near infrared energy in whatever from the water may be, okay, in soil, leaves, lakes, rivers, etc. And absorption in 20 centimeter depth. The meaning is that if we plot the reflectance versus wavelength curve in case of water, then if it is red band, let's say 0.7 micrometer, clear water 0.4, it's 0.5, it is 0.6. Okay. So water absorbs near infrared energy. It means wavelength more than 0.7 micrometer. It is a near infrared band. Water absorbs the entire energy. It is a property of water. Okay. And in whatever form it is present, like if it is in lake, river, if it is with leaves, or if it is within the soil, okay, and absorption in 20 centimeter depth. We can say that it is transmitted till 20 centimeter and it is then absorbed. In the figure, you can say that water bodies which are located using infrared band, they are black in color. Why? These are the water bodies. They are shown black in color. Why it is so?
Sir, in IR, heat is measured, so it is very cold.
Because of deep water, it
It
absorbs all
is
energy.
not like that. Yeah, if we have a water body, we say that depth will be more than 20 centimeters is very low depth. Okay. So if we have a water bodies like pond, river, ocean, so in that case, what will happen? All the wavelength which are in NIR band are more than that. We can say lambda more than 3.7 micrometer. They are completely absorbed within the water. Okay. When we analyze the reflected energy, let's say if we define one ground resolution cell within the water body, so what sensor does? If let's say our sensor is operating in NIR band, the sensor is operating within NIR band, the total upgoing energy from the ground cell, yeah, we can also say it grid, what it will be? Nothing. It will be very less. If water absorb, then there will not be the return. There will not be the reflected energy. So what will happen? Let's say if energy is very low, we can say close to zero. So for this energy, the low dn value is assigned, and obviously if E is equal to 0, dn will be 0. Okay. And the lowest dn value is assigned black color. Just see over here in the image, in the grayscale image, water bodies are shown black in color. This part will be discussed later on, like what is the algorithm to map energy in dn values and then further dn to assignment of a particular shade of gray color.
सर सर जो आपने सर जो आपने पहला
See,
हेलो
please listen. I will give you time to ask the query. Okay. In the middle of the lecture, I will give you time to ask the query. In that time frame, you can ask. Fine. Let me complete this first. So the water bodies are located using IR band, and the black color is given to them. Why it is so?
Sir, can you explain it again? Because sir, how the energy becomes zero, like the lowest energy, sir, वो point थोड़ा clear नहीं हुआ.
नहीं, मैंने आपको यहाँ बताया ना कि ये मैं बाद में बताऊंगा इसको. It is just for the brief understanding over here.
Okay.
सुना नहीं आपने क्या?
नहीं सुना सर, but
इसको मैं बाद में बताऊंगा. It is for the brief understanding over here. I will come to this point when I will discuss about the platform and how data is acquired. And there I will say that, okay, in one particular lecture, I discussed about this, and I'm revisiting the detailed discussion on this concept.
Okay, sir.
At this point of time, just you need to keep in mind when the reflectance is very low, or it is close to zero, like in this case. In an IR band, water completely absorbs the energy, so we don't have any reflected energy. But still, for this pixel, what sensor does? Sensor sense the energy is equal to zero, because there is no reflected energy. So if sensor sense it as is equal to zero, okay. So in that case, what will happen? The lowest energy will be given lowest dn number, and highest energy will be given highest dn number. This is the mapping we do. And this mapping, how it is done, it will be discussed later on. Okay, in the next lecture, in that particular chapter. When dn is zero, then there is a algorithm through which we assign color to the grid. We can give a color to the DN number. So the lowest DN number 0 in grayscale image, and the highest, if it is 8-bit image, then we have a DN 255. This is the highest DN number. For this we assign white in color. Okay. In the second image, it is acquired from the same area. Just see. The infrared band can be used to determine the physical characteristic of the water body, that is turbidity. Turbidity means if water gets turbid due to the soil content, we can say, or due to the sand content. Please wait.